Right, we're going to have a quick look at specific heat capacity. We're going to do two things. We're going to define it and calculate it, first of all. But the main thing we're going to do is calculate the final temperature of a bunch of different materials when they reach what's known as thermal equilibrium. Off we go. So, this is the equation for specific heat capacity, which you can use to define it. Specific heat capacity, this C in the middle, is a constant for any given material. It's the amount of energy it takes to heat up a certain mass of a substance by a certain temperature. The units for C are joules per kilogram per Kelvin. You can also use per degrees centigrade, but generally Kelvin's a good one to use in thermodynamics because it's really important by the time you get to the gas laws. So it's the amount of energy it takes to heat up a mass of a given substance. For example, water is about 4,200 joules per kilogram per Kelvin by a certain temperature. It's one of the two equations you learn at the beginning of thermodynamics. This equation, the top one, specific heat capacity, is involved in changing the temperature. So in these sections here, when you're heating up a solid, a liquid, or a gas, you would use equation number 1. However, if you're changing state, melting or boiling, you would use equation number 2 for latent heat capacity. So that's the two main equations at the start of thermodynamics. Here's the question. It's quite difficult to visualize, so you might want to draw yourself a diagram. You've got an iron cube with a certain mass, and it's quite hot, so the same boiling temperature of water. It's then removed and placed into an aluminium container filled with water, and they're both at 20 degrees C. So what you've got to figure out is what temperature will everything be when it reaches thermal equilibrium. So if you want to pause it, there's some data here. You can try and work out the question, and then I'll go through the solution. So here's the solution. We've got our iron cube, and we're dropping it into a calorimeter, effectively, just an aluminium container filled with water. So in order to reach thermal equilibrium, we're going to have to transfer energy from the iron. That's kind of the definition of thermal equilibrium. It's when there's no more energy being transferred between the iron and the other substances. So the iron is going to lose energy, and the water and the aluminium are going to gain all that energy. There's meant to be some aluminium here defining what thermal equilibrium is, but it'll crop up in a minute. Blooming animations there. So here we go. We've got the equation using the data for iron here, and the iron is going to cool down to its final temperature. It's starting at 100, but it's really going to reach its TF, its final temperature, when it's transferred all of its energy to reach the same temperature as water. So this is the data for water. Water is actually going to heat up when the iron gives it energy, and then the aluminium here is also going to heat up. So what we've seen here is essentially me just multiplying out the beginning of the equation in each case, and then if we multiply that out again, I've deliberately kept the TFs in blue. So I multiplied out the brackets, so that's why I have 286 TF here. It's 286 multiplied by TF, or 1046 multiplied by TF. And you can kind of see where this is going. We're going to move all of the TFs over to one side and all the other numbers to the other side. Resolve all that nonsense, and then we're going to do a quick bit of algebra to figure out if we divide the green number by the blue number, we should end up with a temperature of about 37 degrees C. And any minute now, yep, there's our definition of thermal equilibrium. No more thermal energy being transferred, and we have just reached that point here at 36.7 degrees. There we go.